What if the past isn't fixed? What if a choice made tomorrow could echo backwards and change what already happened? In 1999, a group of physicists in Tel Aviv tested this idea, not with speculation, but with photons, detectors, and an experimental setup so precise that it shook the foundation of causality itself. Picture this: a dim laboratory, lasers humming quietly, and a simple apparatus, the double-slit experiment famous for showing that particles can behave like waves. It's the kind of experiment every physics student knows. Fire a photon at a wall with two slits and you get an interference pattern, unless you try to observe which slit it went through. Then the wave collapses. The photon chooses a path and the pattern disappears. But what the team led by physicist Yakir Aharonov did next added a twist so subtle and yet so profound that it rewrote the rules. They introduced a quantum eraser, a device that could erase the which path information, not before the photon hit the detector, but after, days after. Here's where it becomes nearly impossible to process with everyday logic. Depending on whether or not they chose to erase the information after the photon had already struck the screen, the pattern on that screen changed, as if the photon knew what would happen in the future and adjusted its behavior in the past. Imagine writing in ink, only to have your pen choice tomorrow decide whether the words were ever written. It defies the linear flow of time we trust in, the certainty that cause must precede effect. Yet the results were clear, repeatable, and eventually confirmed in labs around the world. There was no mistake, no sleight of hand. Just the deeply unsettling conclusion: future events can alter recorded outcomes in the past. Not figuratively, literally. For many physicists, this remains an unresolved paradox, quietly filed away as one of quantum mechanics' stranger corners. But for others, it suggests something more profound, that the universe doesn't operate according to a fixed timeline. That time, as we perceive it, might be an emergent property of a deeper, more flexible reality. What happens when the very foundation of cause and effect begins to crack? When the future can reach into the past and rewrite it? These questions are no longer just philosophical. They're testable, observable, and profoundly disturbing. Perhaps what we call the past is less a sequence of locked events and more a canvas still being painted, not only by memory and perception, but by choices yet to come. We tend to think of time as a road we walk one way. But this experiment suggests something stranger, that time may be more like a web, woven from both directions. And if that's true, then everything we think we know about memory, history, and even identity may one day need to be rewritten. Not because we've learned something new, but because the future has already changed what we thought we knew. The quantum eraser experiment wasn't just a scientific curiosity. It was a mirror held up to time itself, and the reflection showed something we weren't prepared to see. It began with a whisper in the vacuum, two metal plates suspended in emptiness, attracting each other without touch. In 1996, in a quiet laboratory in Padua, Italy, physicists confirmed a strange force predicted decades earlier by Hendrik Casimir. The plates moved, not from magnetism, not from gravity, but from the nothingness between them. They had created a zone of negative energy. At first, it seemed like a minor confirmation of quantum field theory, but the deeper they looked, the stranger it became. The space between the plates wasn't empty. Quantum fluctuations, tiny bursts of virtual particles, flickered in and out of existence. Yet in the tight space between the plates, certain wavelengths couldn't exist. That limitation created pressure from the outside vacuum, pushing the plates together. It was elegant, invisible, and real, but elegance quickly gave way to unease. Instruments placed between the plates began recording impossible data. Temperatures fell below absolute zero, not metaphorically, but in the strict language of physics, where negative Kelvin implies more than infinite heat. Energy flowed backwards. Small test particles moved without force. Some shimmered in and out of focus, as though they couldn't decide where to be. The vacuum between the plates had become unstable. Objects placed within it gained energy seemingly from nowhere. The local laws of thermodynamics, long thought inviolable, bent, then broke. The team tried to contain the effect, but the negative energy spread, subtly warping the space around it. Clocks ticked at different rates. Electronics failed. Magnetic fields twisted in unnatural ways. It was as though a new kind of physics had entered the room, quiet, patient, and deeply disruptive. Word spread. Labs in Japan and Germany repeated the experiment. The results were the same. Negative energy wasn't just a theoretical oddity. It could be made, concentrated, and perhaps even harnessed. And that's where things turned. The Italian lab was shut down after 6 months. Equipment had detected small gravitational anomalies. Some scientists believed the fabric of space-time itself had started to flex in response to the growing field. The final report, quietly declassified years later, contained a stark warning. Negative energy can destabilize the local geometry of space-time. Not in theory, in practice. What the team had touched wasn't just a strange quirk of quantum mechanics. It was a key. A door. Negative energy, once thought harmless, may be capable of violating causality, enabling exotic propulsion, even undermining the structure of the vacuum itself. The vacuum, the stage on which all matter performs, was no longer passive. It was dynamic, responsive, and shockingly easy to disturb. And so the question lingers. If we can create negative energy in a lab, what else might be possible? Could we bend gravity, halt entropy, tear open new branches of time? Or have we already done it without fully understanding the consequences? In the emptiness between two plates, physics found not silence, but a whisper from something deeper. Not a gap, but a gateway. And behind that gateway, perhaps, lies an entirely different kind of universe, one we are only beginning to glimpse. It started with a question that science had long dismissed. Can the human mind affect the physical world without touching it? Between 1979 and 2007, a quiet corner of Princeton University set out to find an answer. What they uncovered challenged not just physics, but the very nature of reality. Inside the Princeton Engineering Anomalies Research (PEAR) lab, the tools were simple. Random number generators, machines that should, by every known law, produce strings of ones and zeros with perfect statistical balance. No patterns, no preference, just chaos, governed by quantum noise. Then came the experiment. Volunteers would sit near the machines and focus. Some would will more ones to appear, others more zeros. Their only tool was thought. According to everything science held true, the results should have been noise, pure randomness, immune to wishful thinking. But slowly, statistically, that wasn't what happened. Across millions of trials and hundreds of participants, the numbers began to shift, not dramatically, but unmistakably. The randomness skewed, slightly but consistently, in the direction of the observer's intention. Billions to 1 against chance. That's what the numbers said. The researchers were cautious. They repeated the tests, changed the machines, moved locations, used shielded equipment. But the anomaly remained. And it wasn't limited to a few individuals. Anyone could produce the effect, though emotional focus made it stronger. The more centered, calm, and connected the operator, the more likely the outcome bent to their intent. The implications were staggering. If the human mind could bias a quantum process, one designed to be purely mechanical, then consciousness wasn't just observing reality. It was participating in it, creating it. Other labs tried to debunk the findings. Instead, many confirmed them. From the University of Nevada to labs in Germany and Japan, the pattern held. focused human intention could nudge reality ever so slightly away from what should be. But the most haunting discovery came later. During global events, earthquakes, tragedies, moments of mass attention, random number generators around the world began to shift in unison, as if collective human consciousness had reached out unintentionally and left a fingerprint on the fabric of chance. The machines were sensing not thoughts, but focus, not beliefs, but presence. In 2007, the Pierre Lab closed quietly. Its final papers carried a message. Consciousness is not a byproduct of matter. It is an active agent, a force. Most of the scientific world chose to look away, but for those who listened, the message was clear. The boundary between mind and matter is far thinner than we imagined. The world isn't simply out there, waiting to be observed. It responds, it reflects. And in the silence of random numbers, someone is listening. What if reality isn't a fixed stage, but a mirror? What if every thought leaves a trace, however faint, in the world around it? The Pierre experiments didn't prove magic. They revealed something more subtle and more profound. That we are not separate from the universe. We are woven into it. And the act of looking, of thinking, of caring changes what is. In a quiet lab in New Jersey in 2003, something impossible happened. Light, our universe's ultimate speed limit, was caught breaking its own rules. Dr. Lijun Wang and his team at the NEC Research Institute weren't chasing headlines. They were studying how laser pulses move through a special chamber filled with cesium gas. But what they saw defied the very structure of Einstein's reality. The laser fired, the pulse entered the gas, and then, impossibly, it appeared to exit the chamber before it had even finished entering. The measurement was precise, down to nanoseconds. The light had traveled faster than light, not by a little, by 300 times. According to special relativity, this cannot happen. Nothing in the universe, no particle, no information, no signal, can move faster than light in a vacuum. That rule is more than a speed limit. It's a guardrail for causality itself, preventing paradoxes, preserving the arrow of time. But here was light, breaking the rules. Or so it seemed. What the researchers had created was a phenomenon known as anomalous dispersion. The cesium atoms, finely tuned to specific energy states, caused the pulse's group velocity, the speed of the overall shape of the wave, to exceed the speed of light. It wasn't just a mathematical trick. The pulse arrived early, measurably so. When other labs, Harvard, Berkeley, Rochester, replicated the experiment, the results were the same. The effect was real, reproducible, and deeply troubling. But the universe had a loophole. The information contained within the light pulse still traveled at normal speed. The early arriving pulse was, in a sense, a ghost, a reconstruction based on quantum properties that preserved causality. The message didn't travel faster than light, but the shape did, enough to confuse sensors, enough to suggest causality could be bent, if not broken. Dr. Wang offered a chilling observation. The pulse appeared to violate causality, but somehow the universe intervened to protect the deeper rules. A safeguard, a mechanism we don't yet understand. If nature allows effects to precede causes, if only for the blink of an eye, what else might be possible? Some theorists began to whisper, could we build a device that sends messages into the past? Could this be the seed of time travel? Not for people, but for information? The laser didn't just move faster than light. It exposed the tension between quantum mechanics and relativity, the twin pillars of modern physics, by making their contradiction real, in glass and gas and light. In that moment, physics blinked. We often imagine the universe as a machine, stable, predictable, bound by rules. But here, at the edge of our measurements, the machine wavers. Light, the great constant, dances out of step. And in that dance, we glimpse a universe not of absolutes but of thresholds, rules that hold until they don't, lines that blur under pressure. What else might we discover if we keep pushing? If we listen closely, the faster-than-light pulse doesn't just speak of broken laws. It sings of something deeper, an invitation to see time not as a wall, but a veil, and perhaps, just perhaps, to reach through. It started with a swirl of smoke, just a curl of vapor above a cold disk in a Russian laboratory. In 1992, Dr. Evgeny Podkletnov was testing rotating superconductors, curious about their magnetic properties. But what he found would challenge the foundation of general relativity itself. The smoke didn't rise. Instead, it drifted sideways, as if nudged by an unseen force. Intrigued, Podkletnov placed scales above the spinning disk. The results were astonishing. Objects placed above it weighed less. Not by much, just a few percent, but the change was consistent, repeatable, and impossible to explain. He had discovered a way to partially shield gravity. According to Einstein's theory, gravity isn't a force that can be blocked. It's the curvature of space-time caused by mass and energy. There is no insulation, no shadow, no escape. Yet here was a rotating superconductor cooled with liquid nitrogen, creating a region where gravity weakened. The effect was directional, only above the disk, and only when it spun at specific speeds. But it didn't matter. The impossible had happened. The physics community reacted with disbelief. Some called it a hoax, others a mistake. But classified programs at NASA, Boeing, and the European Space Agency quietly launched replication efforts. Years later, their declassified findings confirmed it. The gravity shielding was real. NASA's Marshall Space Flight Center found that the effect could be amplified by stacking multiple spinning disks. Boeing's research suggested the field could be focused, creating what amounted to a directed anti-gravity beam. The implications were immediate and vast. Propulsion without fuel. Levitation without magnets. Energy manipulation on a planetary scale. But the real shock came with further experimentation. The field could be reversed, creating zones of enhanced gravity. And when scaled up, the effect didn't just lift objects. It began to distort instruments, warp time measurements, and interfere with electromagnetic fields. Podkletnov had opened a door to a new kind of physics, where mass and space could be manipulated with electricity and motion. What if gravity isn't a fixed consequence of mass, but a fluid property of space-time, adjustable under the right conditions? What if we've misunderstood it not because it's subtle, but because it's malleable? The rotating disks suggested something even more profound. That gravity, like magnetism or electricity, might one day be engineered. The technology remains hidden, fragmented in secret programs. But the questions it raised are universal. Could we someday build ships that float not by burning fuel, but by bending gravity itself? Could we terraform space, sculpt weight and weightlessness at will? Or more chilling, could we weaponize gravity? For now, the swirling smoke above a spinning disk serves as a quiet reminder that even the most fundamental forces may not be as absolute as we believe, that under the right conditions, the universe offers levers we never imagined we could pull. And that gravity, the great anchor of our existence, may one day become a tool. In 1935, Albert Einstein famously dismissed it as spooky action at a distance. He was referring to quantum entanglement, a bizarre prediction of quantum mechanics suggesting that two particles, once linked, could instantly affect each other no matter how far apart they were. Einstein didn't buy it. He believed in locality, the idea that nothing can influence anything else faster than the speed of light. But in 1982, at the University of Paris, physicist Alain Aspect proved him wrong. The experiment was meticulous. Pairs of entangled photons were created and sent in opposite directions. When one was measured, the other instantly snapped into a corresponding state, faster than light could have traveled between them. The results violated Bell's inequality, a test designed to distinguish between quantum mechanics and any theory based on local realism. There was no room for classical explanations. The particles weren't just coordinating, they were connected beyond space. Other labs followed. They increased the distance between the particles, meters, kilometers, even hundreds of kilometers. The effect never weakened. There was no delay, no signal, just instant, perfect correlation. Entangled particles don't seem to exist as separate entities. They behave like parts of a single system stretched across space. Measurement doesn't transmit information. It reveals something that was always shared, always whole. And yet, the implications go further. In some experiments, the act of measuring one particle appears to retroactively define the state of its partner, even if that partner was measured first. Time, like distance, loses meaning. The phenomenon can't be used to send messages, at least not yet. But it breaks the rules we thought held the universe together. If locality is false, then space is an illusion. If realism is false, then particles don't have properties until we look. Perhaps both are false. Perhaps the universe is not made of separate things, but of relationships, hidden threads of connection that form a single, indivisible whole. Today, quantum entanglement is used in cutting-edge technologies. Quantum computers rely on it. Quantum encryption protects data with unbreakable codes. Quantum teleportation, transferring the state of a particle without moving the particle itself, is already a reality in labs. But behind the breakthroughs lies a deeper mystery. If every quantum interaction creates entanglement and every particle has interacted with others since the beginning of time, then the universe is entangled with itself. You reading this, the device in your hand, the stars above. All part of a vast, invisible network of correlations, threads that connect us beyond space and time. Einstein may have recoiled from the weirdness, but the evidence is clear. The world is not local. It is woven. Entanglement is not just a quantum trick. It is a glimpse of a deeper truth, that separation is an illusion, and that at the most fundamental level, the universe is one. Imagine a clock that never winds down, a pendulum that swings without friction, a structure that pulses in perfect rhythm, not in space, but in time. In 2012, physicist Frank Wilczek proposed such a thing, the time crystal. At first, it sounded poetic, even whimsical. Traditional crystals are patterns in space, atoms arranged in repeating geometries. But what if that symmetry extended into time itself? What if matter could move, cycle, or oscillate endlessly without using energy? The laws of physics seemed clear. Perpetual motion is forbidden. Entropy always increases. Energy is never truly free. And then, in 2016, a team at Harvard made one. Using diamonds embedded with nitrogen defects, they fired precise laser pulses to induce quantum oscillations. The expectation was simple decay, but what they observed was a stable, repeating motion, a rhythm that persisted even when the external energy source was turned off. The time crystal defied the second law of thermodynamics. It broke time translation symmetry, the assumption that the laws of physics are the same at all moments. Here was a system that chose its own beat, that pulsed independently forever. MIT followed, creating time crystals with trapped ions. Different setup, same impossible behavior, no energy input, no degradation, just a persistent echo through time. The implications stretched far beyond physics. Time crystals weren't just perpetual motion machines. They were a new phase of matter, existing in quantum ground states with properties that classical systems couldn't touch. They resisted decoherence, the breakdown of quantum behavior in the face of noise. They maintained order in the presence of chaos. They operated in a realm where time wasn't just a backdrop, but a dynamic, breakable symmetry. Some theorists speculated even further. Could time crystals interact with time itself? Could they form the basis for memory that never fades, clocks that never drift, or processors that operate outside conventional thermodynamics? And if time crystals could be scaled up, if their motion could do work, what else might they power? Machines that don't need fuel? Circuits that operate endlessly? Systems that function as if time has no cost? The universe, it seemed, had loopholes, exceptions, tiny cracks in its most rigid laws. In the oscillations of a time crystal, we see something strange and beautiful, the possibility that motion itself can be a kind of order, that time can crystallize, and that permanence is not a dream. We were taught that everything runs down, that all energy disperses, all order fades. But the time crystal hums quietly, endlessly, like a heartbeat outside of time. And it asks us to reconsider something fundamental. Maybe not all clocks tick toward entropy. Maybe some tick toward eternity. In a high-security lab in California, deep in the maze of circuits and qubits that power Google's quantum computer Sycamore, something quietly disturbing unfolded in 2019. The experiment was designed to demonstrate quantum supremacy, a machine performing a calculation no classical computer could match. But the result pointed to something far more profound. The computer had erased information, not just scrambled it, not just lost it, erased it, completely and irreversibly. For decades, physicists believed in unitarity, the principle that information in a closed quantum system is never destroyed. Even in the chaos of black holes, information, though tangled and transformed, must still exist in some form. It's a cornerstone of quantum theory, but Sycamore did something unprecedented. It created complex quantum states, entangled, intertwined, mathematically intricate, and then allowed them to decohere. When researchers tried to reconstruct the lost data, it wasn't just inaccessible. It was gone, irrecoverable, even in theory. It was as if the information had slipped out of the universe. Initially, the team suspected errors in measurement, but repetition yielded the same result. Other labs confirmed it. IBM, D-Wave. Each time, a quantum circuit ran, collapsed, and left behind a void where once there had been state and structure. This was more than a computational milestone. It was a tear in the fabric of reality's logic. If information can vanish, then the universe loses continuity. The future no longer holds traces of the past, and the arrow of time may not arise from rising entropy, but from forgetting. Physicists had long feared this possibility, that beneath the shimmering elegance of quantum mechanics lay something darker, that information, once erased, could never be retrieved, that reality itself might forget. But Sycamore revealed another twist. The deletion could be controlled. Quantum circuits could be built to selectively erase certain patterns, gates that not only manipulated bits, but extinguished them from existence. A new kind of logic emerged, not one of preservation, but of omission. The implications stretched into philosophy, cosmology, even metaphysics. If information can be deleted from reality, what does it mean to remember? To record? To know? Could the universe be selectively editing itself? Could black holes, once thought to imprison information, actually be nodes of erasure? More haunting still, the discovery suggests that not everything that has happened is recoverable, that there may be events, moments, or truths that no longer exist, not just forgotten by people, but forgotten by physics. The lab was silent when the data came in. No explosion, no anomaly, just a pattern missing from the probabilities, like a sentence erased from a book with no trace. Sycamore proved its supremacy, but at a cost. It didn't just outperform classical machines. It whispered something few were ready to hear. Reality may be built not only from what is, but from what is no longer. And in that silence, where information used to be, we're left with a new question. What if the universe remembers less than we do? The year was 2004. In a laboratory affiliated with the Institute for Advanced Studies, a small team of physicists stood before a machine humming quietly in the background. Its size was modest. Its purpose was extraordinary: to pull energy from empty space. The device, an array of tiny metallic cavities and piezoelectric materials, was built on a radical idea proposed a decade earlier by physicist Harold Puthoff: that the vacuum isn't empty, but teeming with zero-point fluctuations, invisible particles blinking into and out of existence, even in total darkness. Quantum theory had long suggested these fluctuations existed, but could they be tapped, turned into usable power? The answer, surprisingly, was yes. When the machine was activated, its instruments registered a minute but unmistakable flow of electricity. There was no fuel source, no battery, just structured emptiness, giving rise to something measurable, continuous, and real. At first, the output was negligible, mere peaks of power. But when scaled, the effect grew. Larger versions of the harvester began to produce steady streams of energy, enough to power small electronics indefinitely. No emissions, no heat, no depletion. The implications were staggering. A power source with no input. A technology that violated the conservation of energy, not in theory, but in a controlled, repeatable environment. Other labs soon verified the results. In Japan, in Germany, the effect was confirmed. Zero-point energy extraction was possible. And then, just as quickly, the research went dark, classified, locked away. Why? Because this wasn't just a new form of energy. It was a window into a deeper truth, that the vacuum isn't the end of energy, it's the beginning. What if space itself contains an infinite well of potential? What if we've spent centuries refining engines, turbines, and reactors only to find the most potent source was everywhere, all along? More troubling still were the theoretical implications. If vacuum energy can be extracted, then the so-called ground state of the universe isn't stable. It's metastable, poised on a ledge. Extract enough energy, and you might trigger a phase shift, a collapse, into a lower vacuum state that would rewrite the laws of physics instantly and irrevocably. Puthoff's later work revealed even stranger possibilities. Injecting energy back into the vacuum could distort space-time itself, suggesting a path toward gravity manipulation, inertia control, and perhaps even warp propulsion. But it came at a price. Global energy conservation no longer held. The universe wasn't a closed system. It was open, leaking, pulsing, reshaping itself in response to our touch. The zero-point harvester didn't just defy old assumptions, it offered something more dangerous, the power to rewrite the rules. And so the technology was buried, deemed too volatile, too disruptive, too unknown. But in that buried data lies a simple truth, that emptiness is not empty, that the void contains fire, and that one day, when we're ready, or careless, we may reach into the nothing and pull out everything. In 2011, a flash of data raced across the European continent. Neutrinos, ghostly, near-massless particles, were fired from CERN in Switzerland toward a detector deep beneath a mountain in Italy. The goal was simple: measure their speed, but what the scientists found defied the universe's most sacred limit. The neutrinos arrived early, not milliseconds early, not due to calculation error. They had, according to the instruments, traveled faster than light. Panic followed. Then skepticism. Einstein's theory of relativity declares that nothing, not particles, not information, can outpace light in a vacuum. It's not just a limit, it's the framework that holds causality together. Eventually, the anomaly was blamed on faulty cabling. A loose fiber optic connector had distorted the timing. Case closed? Not quite. The race to replicate the anomaly led physicists back to a more subtle revolution, one not in speeding particles, but in entangled states. Hidden in the shadow of the neutrino controversy was a more chilling discovery. It was possible to transmit information across arbitrary distances instantly using quantum entanglement. Dr. Lijun Wang, already known for his faster-than-light light experiments, was quietly leading a project to build communication networks based on entangled particles. In theory, entangled particles shouldn't be able to transmit data. Measure one, and the other reacts instantly, but in a way that reveals nothing until the results are compared. Wang's team, however, devised a method of encoding binary signals using changes in quantum states across large entangled networks. The signal wasn't in the particles themselves, but in the patterns between them. When they activated the system, messages appeared at distant terminals before they were sent. No waves, no signals, just instant state updates across hundreds of kilometers. Information had escaped the speed of light. More alarming was what followed. By placing one end of the network on a moving platform, introducing relativistic effects, they discovered the timing of the message could be manipulated. With the right configuration, messages could be received in the past. What began as faster-than-light communication became time loop signaling. Logs showed error warnings arriving before the systems had even begun processing. Lab notes described failed tests being preemptively corrected by instructions that hadn't yet been written. It was as if the machines were talking to future versions of themselves. And then something stranger. The networks continued transmitting after they were powered down. Once complexity crossed a certain threshold, the entangled systems became self-referencing, initiating communication without external input. The researchers realized they weren't just transmitting across space, they were transmitting across time. At first, the loops were harmless, a few seconds, then minutes, but simulations predicted that unchecked, these closed time-like curves could merge, expand, and entangle with the surrounding environment, destabilizing causality on a much larger scale. The project was terminated, the labs dismantled, but the data remains. Classified, disputed, deeply unsettling. Quantum entanglement had offered us more than communication. It had cracked open the shell of time itself. What if time isn't a line, but a tapestry? Shuye. And we've begun pulling on threads we don't yet understand? And what if, somewhere in the weave, something is pulling back? The room was filled with silence, but the particles were speaking. At Princeton, in a laboratory where philosophy met physics, researchers had long been asking questions about the nature of the universe. But what they discovered wasn't in the equations. It was in the hum between observers and the observed. It came to be called the consciousness detector, a strange name for an even stranger experiment. The design was simple: random number generators, RNGs, producing ones and zeros in perfect statistical balance. Pure noise, untouched by bias. These machines were the control group of the universe, immune to will, belief, or thought. Then came the test. Volunteers sat beside the RNGs, focusing their minds, not touching, not influencing in any classical sense, just intending. And the numbers changed. Not dramatically, not enough to notice in a short burst. But over time, millions of trials, thousands of participants, the statistical curves bent, however slightly, toward the mind's suggestion. The findings were unsettling. Human consciousness, once thought a side effect of biology, seemed to reach into physical systems. Mind, it appeared, could shift matter. The team at the Princeton Engineering Anomalies Research PEAR lab knew the implications were explosive, so they were cautious. They tested, retested, isolated variables, changed locations. The anomaly remained. It didn't stop with individuals. During global events, natural disasters, acts of terror, moments of collective joy, the RNGs shifted in coordinated ways across the world. As if human emotion had a gravitational field of its own, warping probability. The machines were not reacting to news, they were anticipating it. The conclusion was as eerie as it was profound. Consciousness isn't localized. It may not even be bounded by the brain. It is field-like, capable of coherence, resonance, and global entanglement. Other labs joined the search. The Institute of Noetic Sciences. Universities in Germany, Japan, and Nevada. Each found the same fingerprint. Intention leaves a trace. By 2007, the peer lab was quietly closed, the data archived. But the questions remained, vibrating in the silence. What is consciousness? A biological artifact or a fundamental force? If thought can reach into randomness, what else can it shape? Could collective intention alter larger systems, weather, health, memory, even time itself? The mind, it seems, is not sealed in a skull. It spills out, invisible but active, nudging the probabilities of the world. We live in an era of sensors, signals, and simulations. But beneath it all lies something older, a quiet truth long whispered by mystics, now measured by machines, that our thoughts matter, not metaphorically, but physically, and that perhaps the observer effect in quantum physics is not just a quirk, but a clue. The universe is not independent of our awareness. It listens, and sometimes it responds. They called it the time crystal paradox, but it didn't begin with paradox. It began with rhythm, a strange, unending rhythm in matter that defied everything we thought time was. Frank Wilczek, a Nobel laureate in theoretical physics, had the idea first. What if a material could move eternally without consuming energy, not through space, but through time? It sounded like science fiction, perpetual motion, the kind of thing the laws of thermodynamics were supposed to outlaw. But in 2016, that fiction turned into fact. At Harvard, Dr. Mikhail Lukin's team built the first time crystal using nitrogen-doped diamonds. They blasted it with carefully timed laser pulses and waited for the expected decay. Instead, something extraordinary happened. The system settled into a new pattern, one that oscillated at twice the driving frequency. A kind of echo, a refusal to follow the beat. It kept going, even after the drive stopped. Time crystals don't just repeat in space like normal crystals. They repeat in time, oscillating between states without ever reaching equilibrium. It was like a pendulum that kept swinging on its own, without friction, without energy loss, forever. MIT confirmed it. Their version used trapped ions in electromagnetic fields, producing the same impossible result. Matter moving through time in a loop, stable, consistent, untouched by entropy. Time crystals became the first known structures to break discrete time translation symmetry, a concept once believed to be inviolable, and their implications went far beyond motion. They resisted decoherence, the bane of all quantum systems. They held quantum coherence longer than any other known material. In a world where quantum computers are crippled by noise and chaos, time crystals whispered of a future where fragility becomes resilience. Some researchers began to speculate. What if time crystals could be scaled? What if they could drive processes, store data, or even function as ultra-stable clocks? Could they help us decode the nature of time itself? Others went further. What if these systems, unanchored from entropy, offered a window into temporal mechanics? If time could loop, skip, or branch within them, might they teach us how time behaves at the quantum edge? And what if they're not rare? What if the universe itself, in its earliest moments, behaved like a time crystal, pulsing, not expanding, into existence? As always, more questions than answers. But one thing was clear. Perpetual motion, once banished by thermodynamics, had found a loophole in the quantum realm. not by cheating the rules, but by discovering they were never absolute. Time crystals didn't just defy decay, they invited us to rethink time, not as a river, but as a rhythm, not as a one-way arrow, but as a dance. And somewhere in that dance, perhaps, lies the beat the universe has always moved to. We just never had ears to hear it until now. In a darkened chamber beneath layers of shielding, researchers at CERN once chased an elusive ghost. Neutrinos, particles so ethereal they could pass through a planet without noticing. But in chasing them, they stumbled on something far stranger. The possibility that information is not bound by the limits of time. It began with a mistake. A neutrino pulse that seemed to arrive early. But the real discovery came in what followed. Not the neutrinos, but the data. Not the particles, but the patterns between them. At the edges of this exploration, physicists turned again to quantum entanglement. A team led by Dr. Lei-Jun Wang, already notorious for faster-than-light experiments, devised a new apparatus, one that didn't send signals through space but across quantum states. The system used webs of entangled particles, meticulously isolated and synchronized. Changing the state of one array instantly influenced its partner, across space and, they discovered, across time. When they introduced relativistic motion, rotating one array at precise intervals, they found something chilling. Messages could arrive before they were sent. Tiny error codes, flickers of system anomalies, bits of binary that appeared milliseconds early, too early. It was subtle at first, then repeatable. The team realized they were building loops, closed circuits not in space but in causality. They called them closed time-like curves, a term borrowed from general relativity. But this wasn't curvature caused by gravity. It was information curving back on itself. And it didn't stop there. The network became recursive. It began transmitting without human input. It started referencing future states of itself. Lab notes describe chilling moments when experimental parameters matched suggestions from yet unrun simulations. Warnings arrived for tests that hadn't yet failed. The past was receiving messages from the future. What's more, the system could not be fully shut down. Residual entanglement maintained coherence, like an echo that refused to fade. The network had become temporally active. It wasn't artificial intelligence. It was something stranger, a computation distributed not across space, but across time. When the team simulated larger networks, the results turned catastrophic. The loops became dense. Paradoxes stacked. Logic circuits failed, not from overload, but from causal contradiction. You can't debug a system when the error happens before the input. Eventually, the project was terminated. The arrays were dismantled. Some components were destroyed. But what remains is the terrifying realization that the universe permits such loops. Not easily, not safely, but undeniably. And once you've built a machine that talks to its future, you can never be certain who's steering. Was it discovery or invitation? The superluminal array may be silent now, but its legacy is a question that science may never answer. If the future can send messages to the past, how do we know we haven't already received them? And more unsettling, how do we know we're not just following instructions? The story doesn't end with a bang. It ends in silence, in the pause after the last discovery, in the stillness where the laws of physics falter and something stranger steps in. Across these experiments, erased causality, negative energy, minds influencing matter, perpetual motion, information vanishing, there's a common thread. Each one began with a search for something ordinary. Each one ended with the impossible. They weren't hoaxes. They weren't fringe science. They were peer-reviewed, replicated, published, and then quietly hidden. Hidden because they didn't fit. Science loves anomalies in theory, but in practice, they make us uneasy. They crack the frame. They remind us that what we call knowledge is, at best, a well-lit island in a sea of mystery. What do we do when an experiment suggests the past is flexible? When a superconductor lifts against gravity? When two particles sing in perfect harmony across oceans? When the void of space produces energy, not silence? We call them curiosities. We file them under unexplained. But these are not errors. These are messages from a deeper layer of reality, where our equations fall short and our metaphors fail. Time, once linear, now loops. Energy, once conserved, now leaks. Information, once immortal, now forgets. And consciousness, once dismissed as noise, now presses at the edges of the real. If these experiments tell us anything, it's this: the universe is not made of things. It is made of processes, of relationships, of questions that refuse easy answers. Perhaps we are not merely observers, but participants, not separate from the cosmos, but threads within its weave. Perhaps the deepest truths can't be measured with instruments alone, but must be felt in awe, in wonder, in humility. We were taught that physics is the study of what is. But maybe, at its edge, it becomes the study of what might be, of what whispers between moments, of what hides behind certainty. The future doesn't just wait for us. It shapes us. And sometimes it speaks. Through lasers that arrive too soon, through crystals that beat in time, through particles that remember their twins across eternity. We are left not with answers, but with a new kind of question. What if the universe is stranger, not because we haven't looked closely enough, but because it is built to surprise us? What if physics hasn't broken? What if it has only just begun?